Welcome back to the DASYLab training. This training will make the most sense if you have watched the previous modules. In the DASYLab Basics Training Module 4, I'll talk about signal analysis functions, data filtering, and data reduction. The signal analysis functions within DASYLab in the signal analysis group include functions for analyzing signals. DASYLab can do frequency computation and manipulation. We can filter the incoming signal, and you can also window it, which is a form of data weighting. You can compute electrical characteristics. You can compute harmonic distortion. You can resample the data. And if you have DASYLab Pro, it includes additional functions like the nth harmonic, FFT filters, FFT max, and the octave third octave filters. We'll start with a basic frequency analysis function. We'll acquire the data from the analog input, use a data window module to apply a windowing algorithm, and to adjust the length of the data vector. We'll use the YT chart to display the FFT, and then a statistical value module set for max position to determine the frequency of the peak amplitude, and we'll display that onto a digital meter. I've started DASYLab with a new worksheet. The first is to create an analog input. So I'll go to the Measurement Computing driver, drag out the analog input. This is still the USB 201. I'm going to collect data from channel 0. It's starting out with 1,000 samples per second and 100 samples per block. That's a good place to start. I'll click OK. The next thing I want to do is actually look at this data so that I know what my data is. I'll create a display module, the YT chart, and I don't need to do any configuration. I'm just going to put it up to one side. This lets me have it as an early diagnosis to ensure that I can see what the data is. And then once I add the other functions and I'm comfortable, I can remove this function. So the first thing to do, whenever you create a new worksheet, is just make sure your data is working. So I'll click Start, and indeed I am seeing data. The amplitude is a little high for this. I can either fix the chart or decrease the data, and it's easy enough to decrease the data. Right now, my function generator is generating a sine wave at about 10 Hertz. So good, I got data. It looks like what I expect it to be. I'll minimize the chart. I want to create from the signal analysis group a data window module. The data window module has two functions. One is to apply a window type. The default is a rectangle window, which is a no operation. It doesn't change the data in any way. And then there are a number of window algorithms that if you need to know what these different window algorithms are, this is another time when clicking on the help will give you the information that you're looking for. What does the rectangle do? What does the Bartlett do? What does the Hamming, Hanning, cosine do? So this is, when I'm talking about FFTs, I can't teach you the fundamentals of frequency analysis. I can show you how to use the FFT functions within DASYLab. And data windowing is a function that allows you to weight the data to minimize the effect of partial cycles in the sample set. And the sample set that DASYLab is going to be working on is the block size. Now you get to define the block size. The window module allows you to change the output block size, and it defaults to 512. Our incoming block size is 100, so we'll start there. Click OK. So now the input of this module is 1,000 samples per second with a block size of 100, and the output will be the same. So the data window module isn't making any changes. The next module is the FFT module, also in the signal analysis group. And you've got 4 choices, whether you want a real FFT, a complex FFT, or a cross spectrum. Click OK. DASYLab defaults to an amplitude spectrum. The FFT math that it uses does not require the data set to be a power of 2 samples. So you can have an arbitrary size data set, or in this case, block. If you find that you've got a strong DC component of your signal, you can tell DASYLab to suppress that. So I'm keeping this the same. The defaults are fine. I'll wire it up. Now I want to visualize the data. The YT chart x-axis is time. The output of the FFT module, the x-axis, has been transformed to be frequency. So I'm going to make a second YT chart to connect it. Again, no changes here. Connect it up. I'll restore it and bring this second YT chart into the recording area. And now you're going to notice at the beginning of the measurement, the second YT chart is showing you seconds. The first YT chart is showing you up to 100 milliseconds, and the second one thinks it's showing you up to 500. Click the Start button, and the x-axis on the second YT chart has been transformed from milliseconds to hertz. And so now that you can see, I've got a signal that's hanging there around 10. Well, that's actually pretty good for my little device. I'm going to turn on a cursor so that we can see, indeed, the frequency is 10 hertz. I'll turn the cursor off and unzoom and change the frequency. So I'll increase the frequency. And you can see that DASYLab is keeping up as the frequency is changed. And I think that my frequency now is about 23. I think I can get it up to 25, 24. So I have maxed out in this range, and again, I will zoom in. I won't zoom in, I'll just turn on the cursor. And the cursor says that my frequency now is 20 hertz. I'm going to change the range on my generator. And now I think that I've got 130 hertz signal coming in. So I'll move the cursor over here, and the frequency on cursor 2 is 120 hertz. My generator is now saying 125. So it's splitting the difference between the 120 and 125 hertz. Now, when we talk about the FFT, one of the questions that we have is, how do I know what the range and the resolution of the data is? So this is the output of the FFT module. The range of the frequency is based on the Nyquist theorem, and sampling at 1,000 samples per second, DASYLab is going to provide you a computation that is half of that sample rate. So it's actually going to give you 0 to 499 hertz. That's one reason why 500 isn't labeled, because we're only going up to 499. The resolution is based on your block size sample rate ratio. So the resolution, we've got 100 samples in a sample rate of 1,000, so the resolution is 10 hertz. And the cursor showed you that. So this is a cursor point, and as I'm moving the cursor, it is moving by point. And I can use my arrow keys to move back one, forward one, well, forward one, back one, and now back. They're overlapped, they're the same value. So that you can see on the cursor that the delta frequency is 10. Now you can visualize this a lot more clearly if you change the line style associated with the YT chart. Click on the paintbrush on the function bar, go to Colors and Lines, and under Input 0, the line style, you go to Column. In earlier releases, this said bar. It is the same function. It is a function that shows you the individual frequency lines. And again, if I turn the cursors on, you're going to see very clearly that my cursors are on adjacent bars 10 hertz apart. Well, I would like a higher resolution, please. I would like a resolution of 1 Hertz. This is where you go back to the data window module, open its properties, and change the block size to 1000. You are not changing the original data. All you're doing is changing how DASYLab has blocked the data so that now the FFT will get a second of data at a time and do the FFT computation on a second of data. I'll close the cursor window, I'll click Start, and a second later I have got the data and it's just much tighter to see. If I zoom in on just the peak, you'll see that I have a single peak right at 125 instead of being split over 2 frequencies. I'm actually impressed with my signal generator that it's giving me 125 Hertz. So there is no, it's a clean signal. It's a very clean sine wave. You don't see any harmonics. You don't see any additional data in there. Unzoom it. So you see just the frequency. Now, if you change the signal that's coming in, if I move to a rectangular waveform, in the rectangular waveform, you're going to see that there are harmonics, so that you have the original signal at 125, and then you've got a secondary signal over here at, let me get right on it. What's I need? 2, 2, 2. So it's at 375 Hertz. So that is actually a very easy function. It gives us a chance to show off some of the features of the YT chart. This is an example now of where autoscaling comes in handy. If I click on the axis button or the axis menu and go to autoscaling, it will autoscale based upon the amplitude of the signal. So each time it updates, the screen will stay substantially the same, but the amplitude value on the y-axis will change. And DASYLab is trying to figure out the right axis to show the data. So the frequency hasn't changed, only the amplitude of the signal has changed. I should do the same thing on the other YT chart just so you can still see that I am doing a square wave. What happens if I change to a triangular waveform? A triangular waveform is a lot more noisy. And so you're not getting a clean peak at each of the dominant frequencies and the harmonic frequencies. You're getting energy around it, and that's because the nature of the signal. This is where I'd recommend you do some reading. And you go to Google and search for FFT analysis and get some information on how this math works. So I'll click Stop. So I said in the slide that I would also let you get DASYLab to give you the value for that peak frequency. You would think a program like this should be able to do it. So I'm going to do that by using the statistical values module. And I'm going to do 2 things. I'm going to grab the maximum, so this is the amplitude value in each block, and then I am going to get the maximum position. This is the x-axis value that is associated with the maximum y value in the block. So I've got the FFT, I will connect. Like the example in Module 3, statistics, you have to branch when you're using the same wire. And I'd like to display this in a digital meter. Add a channel to the digital meter, start it up, restore everything, bring the digital meter over here. Oh, let's put it here, and click Start. And now what I have 63 Hertz. I'm looking over my shoulder at my signal generator. I'm moving it around, 39 Hertz. I'll change the signal back to the clean sine wave. Frequency doesn't change. The signal did. And so you can see as I am moving around, the value is changing, the amplitude has changed, and the FFT is still being computed. You can see what the amplitude of the peak frequency is and the value of the peak frequency in hertz. So that's a real quick introduction to these functions. The next thing to do is to understand a little bit about how the data window affects you and why you want to use it. And I do that by adding another window, another YT chart. So I'm going to copy the YT chart and paste it in. So now I've got two YT charts, my raw data and my windowed data. So I've hidden the other displays just to show you this. So my raw data is a sinusoidal wave, and now my window data, this is 100 milliseconds of data, this is 1,000 milliseconds of data. I can zoom in and certainly see that it's the same signal once I am looking at the same interval. All right, I'll zoom out again because what I want you to see is how the window functions work. I'll open the properties for the data window by double-clicking on it. You can't right-click while you're running. And I'm going to change the window. The Bartlett is a triangle, and you'll see that really visually on the screen. So when you apply the Bartlett window, what it's going to do is it's going to weight the data at the beginning of the block and at the end of the block to minimize the effect of what might be partial cycles. And it will emphasize the amplitude in the center of the block to offset the weighting that you did at the beginning of the block. So the triangle is kind of clear. It's worth, if you don't know what you need to use, working your way through the different functions. For example, doing a Hanning window. And the Hanning window is a cosine type function. So you see that it's rounded up. This is all depending on what you need for your analysis. So I changed the window to a Hanning-Poisson, and I gave it a parameter of 2, so I got that. And now if I change it to, say, 0.5, then I'll get something that is more similar to the original Hanning window. So again, I'm not going to teach you about the math and the underlying analysis. What I'm showing you is how to use these functions within DASYLab. The difference, let's get the YT charts back, there we go. So now I've got this window function applied, and how did it change my analysis? I've still got 87 Hertz. It looks a little bit cleaner. More of the energy is focused on the peak. Open that up again. I'll change it back to a rectangle. And remember, on the rectangle, the peak wasn't as high and there was energy in the adjacent frequency lines. So the data window is allowing you to compute more tightly and get what should be a more accurate frequency analysis. Stop the measurement and then save this worksheet as FFT so that we can come back to it later. Now let's take a look at the digital filter module and compare it to how the average module works. I want to create an analog input module, and I'm going to add 60 cycles sine wave from the generator module to simulate some 60 cycle noise. We'll add your analog input and the noise together and apply a 60 Hertz low pass filter to try and remove that again. We'll also, in parallel, create an average module, doing a running average, and do a data window FFT and then display it on the YT chart to show you the difference between the unfiltered data and the filtered data. I've saved this worksheet, so now I'll do File New to create a new worksheet. You'll note that DASYLab doesn't have a close function. It just uses File New to clear the work area and memory so that you can start on a new worksheet. Now we're going to create an analog input module again. Still my USB 201. The next thing I want to create is a generator module from the control group. So the generator will create data. I'm going to do this without modulation because I want to create a 60 cycle sinusoidal wave. So sine wave at 60 cycles. I'm going to be combining this data with the analog input, so I need to ensure that the timing matches. I'll click on the time-based button in the lower right and change the time-based settings to match the USB 201 device 1 input HW. Click OK. I also don't want a really high amplitude, so I'll just use 0.5 for the 60 cycle interference. I'll click OK. We're going to add these two signals together using a different mathematics module. I'm going to use the arithmetic module. And the arithmetic module gives you 4 options. You can do single channel with a constant. You can do 2-channel operations, or you can do multiple channel operations. We'll want to add 2 channels together, so I'll just say operations with 2 channels. It defaults to channel plus channel. That's what I wanted, and I will wire this up. And I would like to look at the data that I am creating. So I'll go to the display group and I'll create a YT chart. YT chart, I'll stick with the defaults, connect it to the output of the arithmetic module, and then I'm going to restore the YT chart and run to see how it looks. So right now this signal is still running higher than plus or minus 5 volts. So I will auto scale the axis using the axis menu. And you can see that I have now got a slightly noisy waveform. Stop the measurement so we can look at it. You can see that it's a little higher here, a little lower here. I'm generating about a 25 hertz waveform right now. So the next step is going to be to apply a digital filter and an average module. So first I will go to the signal analysis group for the digital filter. And the digital filter allows me to apply a low-pass 60 cycle filter. And I'm going to leave it at the default filter order of 2. It has standard Butterworth, Bessel, Chebyshev half, and Chebyshev 2. Again, these are standard throughout the industry. If you were to look them up using Google, you would find what the math is behind them. I'll branch to the digital filter, and then I'm going to go down to the data reduction group and pull out an average module. So average is in data reduction because it has the ability to downsample the data. A standard average, for example, take 4 samples, average them together, and output 1 sample for every 4. It also has a mode that allows you to do a moving average. And you can do a moving average, for example, over, let's do 16 samples. And so the input and the output time stream are the same. What will be different is that the output value will be a moving average of the previous 16 values. Branch to this. Now I want to do the same thing I just did in the FFT example. So I'll go to the signal analysis group. I'll create a data window. And there are 3 channels that I want to look at. I want to look at my raw data. I want to look at my filter data and my average data. I need to change the block size here. When I use this, it defaults to 512. I'm going to use the same 1000 that we used previously so that we've got one frequency, 1 hertz resolution. I need to do that for all 3 channels. Now you note that I'm typing, but the module does have a drop-down, and you could select 1000 from the drop-down. Click OK. Now I need to connect the raw data. I need to connect the filter data, and I need to connect the average data. Next, I want to do an FFT. I'll use the same FFT settings. I'll do a real FFT of a real signal. I want to add the channels, and I'm not going to do anything else in here, so we're sticking with the defaults for each of the channels. I want to visualize the data, and I'm going to visualize the data on a YT chart again. So I'll open the display group, pull out a YT chart, and this time I need 3 channels on it. I already know I want to auto scale. I can click that here. Click OK, connect it up. Now I'll restore the displays and find the new chart display. So this is going to initially be all 3 channels overlapped. When I click Start, what I'm seeing now is all 3 channels overlapped. I can make this chart bigger so that we can see it. So what we're trying to do is see what's the difference between filtering and averaging. I'm going to do multiple windows so that you can see this. The raw data has got your data signal, and it's got a 60 cycle blip that's about half a volt. The filter data has got a smaller blip on it, and the average data has got a smaller peak, but the 60 cycle is gone. Now I'm going to change the frequency. Let's decrease the frequency. And depending on the frequency, you're seeing pretty much the same thing. If I start to increase the frequency, so this is, let me go bigger and come back. All right, so you can see that even with a low-pass filter, my data above 60 is coming through, but the filtered data is damping both the primary peak and the 60 cycle peak. If I drop my data below 60 hertz, you'll see that the magnitude of the 60 hertz signal is damped a bit. One of the things you can do while you're running is modify the digital filter. So it's a low pass filter. I'm going to make it a stronger filter by going all the way to a filter order of 10. And when you can do that, you can see that there's still some energy left from the 60 cycle signal. Look at this with the data window. The amplitude is not much diminished from the data that we're generating. So filtering failed. If I change the digital filter to, say, a 70 hertz filter, again, low pass, it is keeping all that energy. Then I will change it down to a 50 hertz filter. And that works to remove substantially all of the 60 cycle interference that I've generated. Now, of course, that depends on the amplitude of the 60 cycle interference that you have. Let me minimize that. But that's just to give you sort of a compare and contrast. The filter module is removing the 60 cycle interference. The average module, averaging over 16 samples, is removing almost all the energy as well, but it also damped the peak. So the peak is running about 6.5. It stated about 6.5 for the filter data, but then it's down to a little over 3. So it's diminished by at least half when you average over it. You can work with different filter types. You can work with different filter frequencies and different filter orders. But this is like the FFT. I can only show you what the DASYLab features are and how to use them, and not necessarily the right filter for your application. That's really going to depend on your sensor and your overall environment. In general, if you've got 60 cycle interference, it makes sense to try to get rid of that before you even acquire the data. We'll come back to this, but one of the things that you can do in the filter is you can use a global variable for the filter frequency. You can also configure, particularly if you're using a global variable, you can configure the module to give you an error if the filter frequency is invalid. And it would be invalid if you've got a filter frequency that isn't compatible with your sample rate or block size. So that just compared a filter function and an average function. Depending on the data that you're looking at, if this were temperature data, this would be perfectly suitable. For vibration data or audio data, you might not want the filter to damp out so much amplitude. Now let's talk about data reduction. DASYLab has a number of different ways to reduce data. In the triggering module, we talked about using a switch and a relay, or a combi trigger and a relay, to reduce the data. This is now looking at the specific data reduction functions in DASYLab: the average module, the separate module, and the merge and display module. And the merge and display isn't so much reducing the number of samples, but rather reducing the number of channels that you see on the screen. As a hands-on exercise, this is a compare and a contrast of different functions for reducing the total amount of data that you are potentially saving to the hard drive. First, create a measurement computing analog input. You'll note that we are continuing to run at 1,000 samples per second with a block size of 100. It is important to remember what your block size is for some of the functions we're going to look at. So what I would like to do is first look at the data. I'm going to display it on a YT chart so that we can see what the original data is. Again, we'll auto scale it because the data has been about 6 volts and the module defaults to 5. And as we've done in previous exercises, the first thing to do is to check that you do indeed still have the data that you were expecting to see. So I still have a sine wave. It's still running at about 6 volts. The next thing, I want to add an average module. So I'll minimize the chart and go to the data reduction group. I'll add an average module from the average or the data reduction group. The average module has got a number of computations that it can do to compute an average: the arithmetic mean, the quadratic mean, a moving root mean square, or the median. The arithmetic mean is the typical thing we think of as average, where you add some number of values, divide by that number, and use that value. A fixed interval structure says take the number of samples listed for the interval width, average those together, and then output the single value result of those 4. Now I'll keep it at 4, and when I do that, I have to think about the block size. The incoming block size is 100. I'm going to downsample that by 4, so I will have 25 samples going out for every 100 that come in. I should change the block length at output to allow DASYLab to fill up the smaller block size, and I'll enter 25. And then the last decision that you have to make is, what timestamp do you want to use the last value or for the block that's coming out. And it defaults to using the timestamp of the first value. Depending on the math or computations that you're doing subsequently, you may want to use the timestamp of the last value of the input block. So just to review, I'm doing an arithmetic mean using a fixed interval structure over 4 samples, and I am changing the block length at output to 25. It came in as 100, and now I'm reducing it by 4. And I'm going to use the timestamp of the last value of the input block. I'll wire that up. Now the nature of the YT chart is that the channels all have to match in time and sample rate. So I'm going to create a second YT chart because now my data is slower in that it's got fewer samples in it. I'll also do auto scaling in this chart. I'll connect it up and restore both charts. So now I'm going to look at my original data and my average data. And what you're going to see is that the average data has got the same interval. We're looking at 100 milliseconds or a tenth of a second worth of data, but the waveform itself looks a little bit jaggier because we've reduced data on it. And if I use the cursor, and what I can do is I can select a cursor and use the arrow key to move it. And the delta t between my samples is showing at 0 seconds. I don't have enough decimals here. So I'll come up here and make this 4 decimals. So the delta t is 0.004 seconds. If I do the same thing on this chart, I'll do the same thing where I'm overlapping the cursor and then using the arrow to move it 1 step away. I have the same problem with decimals, and I'll do 5 decimals. So now that they're a millisecond apart, so 1/1000th of a second apart. So this is 1,000 samples per second. This is now 250 samples per second. I can also do that while I am running, just to verify with DASYLab. If I move the chart out of the way, I click Start. If I click on the wire coming out of the analog input, it tells me that I have a block size of 100. Move this up out of the way too. I have a block size of 100 coming out of the analog input and a sample rate of 1,000. Coming out of the average module, I've got a block size of 25 and a sample rate of 250. Now stop the measurement, minimize the displays, and I want to add another data reduction module, the separate module. I'll drag separate out. Separate allows you to reduce data by removing data as opposed to averaging. So the data that you keep will be unchanged. You can remove data by block or you can remove data by values. If we start with removing data by values, this defaults to keeping a sample for every 10. So you'll skip 9, keep 1, skip 9, keep 1. And in doing that, we are reducing the amount of data by 10. You're starting with a block size of 100, so the output block size should also be reduced by 10. I'll click OK. We'll create yet another YT chart, but first wire it up by branching the analog input. I'll go to the display group and create another YT chart. Auto scale it, click OK, and then connect the separate to the new YT chart. I'll restore all the charts. I'm going to rearrange. There's raw data, averaged data up on top, and separated data below. I'll click Start. And now what you're going to see is the average module retained the signal, but it just looks a little bit choppier. The data reduced looks much more distorted. I'll stop the measurement. So instead of, it looks like we're getting the same frequency on the waveform, but we're not getting anything that resembles the sine wave. It looks just much jaggier. I'll do the same thing I did. This is a 10 times reduction now. So I will put the cursor bars on adjacent samples, and it says the DT is 1/10 of a second or the frequency is 100 hertz. So we averaged to 250 hertz. We separated down to 100 hertz, and we're looking at the same interval on the screen. We're still looking at 100 milliseconds worth of data. We're just seeing fewer samples in all of that data. So this is a way to reduce the total amount of data. Again, it's going to depend on whether you need to retain your waveform, in which case you would probably use average, or you just simply want to reduce the total amount of data without changing the maxima and the minima of your signal. I suppose one other thing to do to compare is to change the average module to averaging over 10 and an output block size of 10. So do the same thing we did in the separate, just to compare. All right, so these distorted as well. So when you take a 100 hertz waveform and reduce the data, you get different results depending on whether you're averaging. We've decreased the overall amplitude to plus or minus 5. And in the YT chart, we haven't decreased the overall amplitude, but we have changed the waveform, and both seem to have retained the frequency of the signal. I'll minimize the displays and add a third function, the multiplex demultiplex function. So this is in this example simply because it's in the data reduction group. It does something completely different. Instead of changing the number of samples in your data stream or in your data channel, it's going to change the number of channels in your data channel. So we're going to multiplex data together, and you have a choice of multiplying by block or per value. And for the example, to be able to demonstrate how it works, I'm going to specify blockwise. So what this will do is it will take two inputs and interleave those inputs so that the first half of its output block will be from channel 0 and the second half will be from its channel 1 input. Now I don't have two inputs to add, so I'm going to add a channel to the analog input. And one thing about the USB 201 is if you have a disconnected channel, as I do, the internal circuitry ends up with a disconnected signal of about 1.75. So click OK, and did something with my wiring, so I fixed that. And I will now take this second channel coming out of the analog input into channel 1 of the multiplexer, and I'll take channel 0 into channel 0, and I'll look at it again in a YT chart. So I'll drag another YT chart out, and I will auto scale it. And restore the displays, but this time the separated data now is going to be on the upper left. I'll click Start, and now what you see in the separated data is two blocks of data in one. The first half of this 100 milliseconds worth of data is showing you that sine wave, and it's a compressed sine wave. So it's the same information that's being shown in the raw data. And then the second half of the block is the 1.75. And this is a flat line. It isn't varying by much. If I minimize the other displays, and I compare. So I'm going to do the same thing by clicking on wires to compare what's happening. The input wire to the multiplexer has a block size of 100 and a sample rate of 1,000. And then we're going to add two channels together but retain the character of it. And DASYLab does that by doubling the block size and doubling the sample rate. So the block size will change by the number of channels that you're multiplexing, and the sample rate will change by the number of channels that you're multiplexing. This is an illusion. We just create a fat block or a fat wire, but there is no indicator in the DASYLab block that this has been a multiplex channel. So you can now use this like any other channel of data, and if you want to break it apart again further into your worksheet, then you could use the multiplex demultiplex to demultiplex it again. And so take the number of channels that you had and take the one wire coming in and output as many wires as you had multiplexed. What this does for a particularly complex worksheet is allow you to combine multiple wires into one wire that you can then route through your worksheet and then break it apart again at another point in your worksheet. It helps manage the complexity of worksheets. To review, we've looked at the signal analysis functions in DASYLab using the FFT and the window module, and we use the YT chart to display the data. We also used a statistics module to pull out the peak frequency in the data. We filtered and averaged the data to remove noise. We reduced the total number of samples in a data channel by averaging and separating the data. And then we looked at managing the complexity of the worksheet with a multiplex module. Module 5 will tackle visualization and making the display look nice. We'll talk about layouts and controlling layouts, and then start to move into DASYLab global variables and strings.